Specifically, in this episode, we're going to look at quantum numbers for multi-electron atoms and how to write the quantum numbers that we have developed based on the wave functions we have described in the previous episode. We'll examine the orbital, spin, and total angular momentum quantum numbers for multi-electron systems. And these are constructed using hydrogen atom 1 electron wave functions. So we'll try to show the connection between the two. The angular momenta of each electron couples with the others. Therefore, we have to understand that these electrons are really not independent of each other as we assumed before. So we're going to perform specific operations to account for this coupling of angular momenta. And so the states together that we generate with coupled angular momenta will explain all the features of the atomic spectra we have observed so far. And so the first, we're going to define the orbital angular momentum quantum number. It's also called the azimuthal quantum number for the multi-electron system. Is denoted with capital L. So the quantum numbers of these multi-electrons systems generated by simple rules. And so we don't want to memorize these rules, but we will take examples and try to familiarize ourselves with the rules. And so the quantum numbers for the multi-electron systems are capitals, uppercase, L, M, S, and MS. These exactly correspond to the corresponding lowercase L, M, S, MS for the 1 electron system. The meaning is exactly the same in each of these cases. So there is a parallel, and this is something we need to recognize between the single electron versus multi-electron systems. The total orbital angular momentum, so we want to pay very close attention to this. Total orbital angular momentum means all the orbital angular momentum summed together. That is M is given by square root L times L plus 1 H cross, or H over 2 pi, where the capital L is the total orbital angular momentum quantum number, or the azimuthal quantum number for the multi-electron system, capital L. So how do we define L? L is your total orbital angular momentum quantum number, and L is given by a simple rule saying that it is starting with L max minus 1, L max minus 2, etc. to L min. So we have not defined what is L max or L min is. So L max is simply the L values of individual electrons present in our system. L1, L2, L3, L4, etc. Okay. So before you do this, there is a very simple shortcut. That is, you do not count any of the paired electrons. Filled shells, ignore them. Only unfilled shells we're going to use. And paired electrons also we don't use because they cancel away the angular momenta, and therefore we only considering partially filled unpaired electrons. So the L values of those are written down. L1, L2, L3, L4 for electron 1, electron 2, electron 3, electron 4. For example, L equals to 0 for 1s, L equals to 0 for 2s, L equals to 1 for 2p, and so on. So if the electron happens to be in 2p, then value of L is 1 for that. So L max is sum of all the L values. L min is simply the largest value of L minus summation of all the remaining L values from it. So that the capital L, the coupled angular momentum, will be all the numbers from L max till L min. So you have all these different angular momentum states are generated by coupling of the existing angular momenta of the unpaired, partially filled orbitals that we have. So let's take an example. What does this mean? P2F1. Let's say you have 2 electrons in the P state and 1 electron in the F state for one particular atom. Doesn't matter what it is. All the other shells are completely filled. So we ignore the full filled shells and we have 2 electrons in the P states. And we know that the 2 electrons cannot be paired. You have 3 P levels, and therefore the 2 electrons will be unpaired. F electron, there are 7 states, and therefore you can have 1 electron unpaired. So we have total 3 electrons that are unpaired. So L for P electrons, 1 is 1. So for the second P electron, L equals to 1. And for the F electron, the third, L equals to 3. So 1, 1, 3. These are the individual L values of the electrons we start with. So L max then equals to summation of all these. 1 plus 1 plus 3 equals to 5. L min, the minimum value of L, is 3, the highest value of L, minus summation of all the others. So 3 minus 1 plus 1, 2. Therefore 3 minus 2 equals to 1. So our capital L will have 5 start with, that is the highest value, 4, 3, 2, and L min, which is 1. So we stop there. So for these 3 electrons with L values 1, 1, and 3, lowercase, we generated angular momentum states of capital L 5, 4, 3, 2, 1. Therefore, we have several total orbital angular momenta that we could generate. A square root of L times L plus 1, where capital L has value 5, 4, 3, 2, 1. So there are all these different angular momentum states generated out of this. Okay, so this is the story. Now, why is this important? So based on the capital L, we make the assignments. If L capital L equals to 0, then it is designated as capital S state. Just as L is equal to, small l equals to 0, we designate it as S state, and small l equals to 1 is designated as the P state in the same way. So we have capital S, capital P, capital D, capital F, capital G states. So these are just as the 1 electron, but this is for multi-electron systems. It's just capitalized in every single case. So this is how you generate the orbital angular momentum quantum numbers. Okay. Then we generate the spin quantum numbers. We have several spins for the multi-electron systems, and so the total spin angular momentum quantum number is simply equal to capital S as a summation of S1, S2, S3, S4, so on and so forth. So each electron can have a plus half spin or a minus half spin. So capital S is simply summation of all these plus halves and minus halves as we do have. Therefore, capital S can be either equal to 0 or greater than 0. So you always preponder the plus halves over the minus halves. That's, if you have a choice, you pick plus half rather than minus half. So at the most, you will have S equals to 0, or it could be S greater than 0. So that's capital S. So that is the total spin angular momentum quantum number. Now we need to calculate this in future. So capital S is important, capital L is important. Then we have total, which is spin plus orbital angular momentum quantum number, J. So as in the other case, 1 electron state, we can have sum of the spin plus orbit angular momentum. And therefore, the quantum number corresponding to that angular momentum is J. J is written in terms of various L and S values. Is written as L plus S minus 1, L plus S minus 2, and so on, up to L minus S. So if once we figured out what is L, what is S, then we can write J values. So they're all rules of writing quantum numbers, and this is how the quantum mechanics postulates the states exist, multiplicities exist, and transitions happen within these states. So these set of rules are generated to explain the atomic spectra, not arbitrarily, but this way. And so let's take an example of L equals to 5 and S equals to 4, for example. Then J will be 5 plus 4, and then 5 plus 4 minus 1, and so on and so forth, until 5 minus 4. 5 minus 4 is 1. So 5 plus 4 is 9. So we have 9, 8, 7, 6, 5, 4, 3, 2, and 1 is the last value, L minus S. So this is, so once we figured out L, capital S values, then we can also then figure out capital J values. We have to remember these rules. And so if L equals to 4 and S equals to 3, then we start with 4 plus 3 and then go all the way 4 minus 3. So 4 plus 3 is 7, then 6, then 5, then 4, then 3, then 2, then 1, the last value of J. So you have that many J values allowed. So corresponding to each of these angular momenta, there will be Z components, of course, and we designate them as we did before, M sub L. That is the Z component orbital angular momentum, M sub L. So that can have 0, plus minus 1, plus minus 2, plus minus 3, plus up to plus minus L values of Z components. These Z components become important when we study the magnetic field effects. And so we need this. So M sub S is a Z component of the spin angular momentum quantum number. And this will have ms1, ms2, ms3, and so on and so forth. And so summation of the Z components of the single electron spin angular momentum quantum numbers. And that goes to 0 for even number of electrons, means the plus and minus cancel away. And for the then M sub J, so the J is a total spin plus orbit angular momentum quantum number. So M sub J will have a J component for the total spin plus orbital angular momentum, and that Z component has a quantum number M sub J that is 0, plus minus 1, plus minus 2, etc., plus minus J for even values of J, or 0, plus minus half, plus minus 3 half, plus minus 5 half, plus minus J for odd values of J. So this is how the numbers work out for these. These Z components are less important right now. We're going to look at them when we look at the magnetic field effects. For now, we're going to pay very close attention to L, S, and J, all capital, for multi-electron systems. So there are certain general rules we obey. The general rules are, in addition to what we just discussed, consider only unpaired electrons and their quantum numbers, because everything else cancels away angular momentum. Closed shells do not contribute to the angular momentum, so ignore the closed shells, as I mentioned before. For greater than one unpaired electron systems, L values are coupled one pair at a time. So if you have one electron, there is nothing. But if you have two electrons, then we need to couple the momenta of the two electrons. And so that's what we're saying. L values should be coupled and one pair at a time. And so the capital L is not to be a negative number. So capital L is equal to L1 plus L2, L1 plus L2 minus 1, L1 plus L2 minus 2, etc., modulus of L1 minus L2. So this is how we generated capital L values. The J values are also given out as L plus A, L plus S minus 1, L plus minus 2 until L minus S, so as we just discussed. So these are the general rules to write the quantum numbers for the multi-electron systems. And so, again, important, all consider only unpaired electrons. Consider only open shells or partially filled shells. And then you write the L, S, and the J quantum numbers as we discussed so far. Then what is called the term symbol is to be written for each state that is available for spectroscopic observation. And that is called 2s plus 1 L sub J. We figured out what is S, we figured out what is L, we figured out what is J. So now you simply write them in terms of 2s plus 1 L sub J as the term symbol. For example, L equals to 0, 1, 2, 3, 4. These are designated S, P, D, F, G. So the central capital L corresponds to this letter S, P, D, F, G, depending on the value of capital L. And we consider unpaired electrons. We don't consider the closed shells. And so then we can write this. So how? So let's take an example of hydrogen atom. 1s1. There's only one electron system. It's 1s, one configuration, electronic configuration. Therefore, n equals to 1, principal quantum number. N equals to 1, L equals to 0 by definition. It's lowercase. If lowercase l equals to 0, capital L also equals to 0. Spin quantum number s is 1/2. Therefore, the total spin quantum number is also capital S, 1/2. So therefore, then J is just a 1/2. So everything is quite simple. So what we have then is 2s plus 1 is 2 times 1/2 plus 1. So that is equal to 2. Then we have L equals to 0 state, that is S. And then we have J value 1/2. So we write 2s 1/2. And it is pronounced as doublet S 1/2. That's how it is pronounced, doublet S 1/2. And now you take 2s1 electron. And if you have 2s1 electron, that's the only electron that is unpaired, unfilled shell, partially filled shell, n equals to 2. L is still equal to 0 because in S state. And then, since lowercase l equals to 0, capital L equals to 0. Since you only have one electron, the spin angular momentum quantum number is 1/2. Therefore, total spin angular momentum quantum number, capital S, is 1/2. Therefore, J is still 1/2. So we still have a doublet S 1/2 state. So it's actually the same as 1s1. 2s1 is same as ns1. Then let's say you have a 2p1. This is the electron in the p state and all the others are filled. Then, since it is 2p, n is 2. Since it is a p, L equals to 1 now. So since L equals to 1, the capital L also equals to 1. And small s is only one electron, so plus 1/2. Then the total spin is capital S is 1/2 as well. And therefore now J needs to be calculated. L plus S all the way to L minus S. So 1 plus 1/2 and 1 minus 1/2. And therefore 1 plus 1/2 and 1 minus 1/2 are the two L plus S and L plus S minus 1 states. So you have two J states. Therefore, you have two terms, two separate terms are produced. And so what are these terms? Doublet. Now, P, because L equals to 1. If L equals to 1 is a P state. And doublet P 3/2. We get 3/2 because J is 3/2. Or it can also be 1/2. So doublet P 1/2. So these are two separate terms for 2p1. So 2p1 has now two separate angular momentum states that we could find out. And if you do a spectroscopy, these terms will be revealed. Means that you'll have transitions from these states into upper states. So you get two sets of lines. That's all it means. And so another example, lithium atom, N equals to 2, L equals to 0, right? And capital L then equals to 0, then small s is 1/2, and then capital S is 1/2, and 2s plus 1 is 2, and J is 1/2. And so N equals to 2, L equals to 1, and L equals to 1, then S equals to 1/2. So we are writing for each of these electrons of different configurations. So now I would ask you to look at the term symbols for atoms with closed shells. And that's given in page 591. And we want you to examine the atomic spectra of one electron systems given on 594 page. And so these terms are written so that we can explain all different sets of atomic absorption spectra recorded in the literature from these elements. And in summary, we have rules to write S, we have rules to write J, we have rules to write L, and how each of these are put together. And we looked at a couple of examples and constructed linear combinations of hydrogen atom one electron wave functions, and from them we have obtained the L, S, and J quantum numbers, all capital, by coupling the angular momenta of each electron with other electrons in a systematic way. And so we have the atomic quantum numbers are then used to assign terms for specific levels in the atoms. Later on, you will see in molecules, we will do the same. So we will apply similar rules and similar term symbols to explain the absorption spectra of molecules as well.